this guest lecture, let me to bring all of you to back to at the end of 2018. We still remember that on 22nd December 2018, the lateral collapse of anak Krakatau, followed by many plume, generated a tsunami that killed nearly 5,000 people and displaced more than 16,000. Our homework are still remain. That's the reason why we invite Dr. Samantha Engwell from British Geological Survey to share her knowledge and to discuss more about the plume of anak Krakatau. Before we start the guest lecture, I would like to inform you that actually this guest lecture is part of our collaboration with many institutions from UK, starting with University of Oxford since 2017, and then followed by many institutions including BGS, University of Birmingham, National Oceanography, etc. The topic for today's session is volcanology. Today we will discuss about the many plume of anak Krakatau. Let me to introduce our invited speaker, Dr. Samantha Engwell. Dr. Samantha, just wait a moment. He got BSc from University of Edinburgh at 2008, and then Master from University of Bristol 2010, and then he got PhD in University of Bristol 2013. Then start from 2015, become senior researcher in British Geological Survey. Okay. Ladies and gentlemen, there will be a short question and answer session at the end of the presentation. To ask the question, the audience may use question and answer feature in the Zoom or write your question in YouTube comment during the presentation. The question should be in the following format: name _ institution _ question. Due to the limitation of time, we will select the question and continue to the remaining if the time is adequate. Before we start the presentation from the invited speaker, I would like to welcome Mr. Agus Muhammad Ramdan, PhD, the Vice Dean of our faculty, to give opening speech. Mr. Agus Muhammad Ramdan, PhD, please welcome.
Terima kasih Pak Mirzam. Thank you, Mirzam. Good afternoon, everyone in Indonesia, and good morning, Samantha. And thank you very much for your willingness to share your knowledge with us this afternoon. We are so lucky that we have Dr. Samantha from the British Geological Survey this afternoon with us. And Dr. Samantha will be talking about volcanic plumes of anak Krakatau, right? I'm a geologist myself, but my specialty is not in volcano. But when it comes to Krakatau, I think all geologists, not only in Indonesia, but also from all around the globe, will pay serious attention due to its gigantic scale of eruption in the past. The most famous eruption, of course, was the one in 1883, if I'm not mistaken. And it is said that the sound of the explosion could be heard around 5 kilometers away from the volcano. Recently, on 22nd of December 2018, as said by Pak Mirzam, we also have tsunami caused by the activity of the anak Krakatau. I think what will be discussed by Dr. Samantha, the volcanic plumes of the anak Krakatau, is very important, not only in terms of the science of the volcanology itself, but also in terms of volcanic hazard mitigations. And without further ado, have a fruitful discussion with Dr. Samantha. And I believe that this talk will serve as excellent food for thought for us this afternoon. And sorry if I cannot attend the discussion till the end of the talk. Thank you very much. Terima kasih.
Yeah. Thank you very much, Pak Agus Muhammad Ramdan. Yeah. Thank you very much, Pak Agus, for the warm greeting for the audience. Without further ado, please welcome Dr. Samantha Engwell from British Geological Survey.
Perfect. Thank you so much for that introduction. Now the difficult bit is working out how to share my screen, so I'll do that right now. I'll move it to the right place. Can everyone see, or can you see my screen?
Yes.
Yes,
Perfect. Okay.
Yeah.
So good afternoon, and thank you for such a wonderful introduction. It's such a pleasure to be able to speak with you today, and particularly about some research that I'm really interested in. So just a bit of background to me. I am a geologist. My background is in geology, and over the years I have focused on volcanoes, and my background is in looking at deposits and looking at the physical characteristics of deposits, and using that information in combination with tools, for example, numerical modelling techniques to try and understand hazard from volcanic eruptions. And so given that, I thought instead of just jumping straight in to talk about Anak Krakatau's plumes, I'd give an introduction as to volcanic ash, why understanding hazard from volcanic ash is important, then talking about volcanic plumes, so how ash gets to where it gets to, and then focusing on the plumes of Anak Krakatau. And if there's any problems at any point, someone just give me a wave and I will try and fix things. Okay, so volcanic ash. So really brief introduction. So volcanic ash is composed of multiple different components. So we have the volcanic glass that's solidified when we have an eruption. We have crystals, and we have lithics. So bits of the volcano that are broken off during the eruption or broken up during the eruption. And volcanic ash is really, really useful. So from a geochemical context, from a petrology context, it allows us, analysis of ash allows us to understand the mechanism of movement of magma through the volcano, to understand the timescales, how long a magma has been in a volcano before it erupts, for example. My background is in physical characteristics and physical dynamics of eruptions. And so what I'm looking at is the grain size of ash, the componentry, the density, the shape of ash, because all of these parameters impact where ash goes during an eruption and how volcanic plumes form. And so just a quick overview as to some volcanic ash impacts, and I'm sure you know lots of these things already, but it leads quite nicely into thinking about volcanic plumes. And of course, there's positive things around living in regions that can be impacted by volcanic ash. It can lead to very fertile soils, for example. Lots of the world's coffee is grown in areas that have been affected by ash. But there are also negative consequences associated with being in an environment that's impacted by ash. And those impacts include health. So for example, on inhalation, particularly with people with breathing difficulties, it can cause issues. With deposition on roofs or on infrastructure, there's potential for damage to buildings. There's potential for impact to agriculture. So for example, by deposition of ash on crops, can cause damage to crops, but also can cause issues for any animals that are feeding on those crops. And that can be related to, for example, the chemical components that are associated with ash that can cause poisoning of those animals. So there are issues around ash. The other main issue related to ash is transport, and that's both on the ground and in the air. And I'm going to expand on that a little bit more now. Just turn off the light.
Sam, excuse me.
Yes.
It is still on the cover, not moving to the next slide.
Oh, sorry?
The slide is
still on the cover. Still on the first slide.
Still on the first slide?
Yes.
Oh, okay. Thank you. Hang on, let me stop sharing.
Yeah.
And I will try and share that again. Thank you for letting me know.
Yeah.
Sorry.
Okay.
You've not missed anything too exciting yet. Right, let's do this again. Apologies for that. Is that any better?
So now we are on the volcanic ash impact.
Yes.
Yeah, okay. Yeah.
Okay,
It's
perfect.
working.
So just so you know what you've missed, a lovely picture of Anak Krakatau. I'll go back to this picture a little bit later. An SEM image of
nice, the volcanic ash.
Of ash, of volcanic ash. This is actually from the Anak 2018 eruption. And then just some images showing what volcanic deposits can look like, a plume, and some people responding to an asheous environment. Thank you very much. Do shout at me if there's any other issues. Okay, so I wanted to briefly mention ash on the ground, impacts of ash on the ground, and because impacts can occur even with quite small amounts of ash. So this is taking some work from Susanna Jenkins and also Tom Wilson. And what they did was analyse the impacts of different thicknesses of ash. And they showed that even with a deposit thickness of 0.5 millimetres, so very, very fine, this is able to obscure road markings and reduce traction on roads. So the implication of even just small amounts of ashfall in populated areas can have quite big impacts. And particularly when we're thinking about, for example, these things happening if we have an evacuation and things like that. When we move up in thickness, so say to 10 millimetres, we're talking about minor damage to buildings, but there are also implications, for example, when we have ash deposition in water treatment centres, or if we have buildings that have air conditioning. So if we have ash that's being brought into buildings, that can be quite big issues. If we start talking about ash of up to 50 millimetres, and to note that this is dry ash as well, then we start to see some of these bigger impacts. So we see a bigger impact to agriculture, potential roof collapse, depending on the type of roofs and things like that. And the reason why it's important to note that this is dry ash is that obviously if the ash is wet, then the load is much greater and therefore damage can occur under smaller amounts of ash. And so these images are some images from ashfall in Montserrat, at Montserrat. So we have ashfall on a building, and then also just ashfall and kind of general devastation to a nearby village. And this happened during eruptions between 1995 and 1997. And then moving on to volcanic ash impacts in the air, and this is something that I do a lot of work with. So if anyone has any specific questions about volcanic ash and aviation, I'm very happy to kind of answer them afterwards, or contact me at a later point. But yes, there are hazards associated with ash in that atmosphere. And so when we have volcanic eruptions, we have ash that gets into the atmosphere and it's able to transport over really large distances. And so a really good example of this, and it's one that I know very well because the UK is not affected by volcanic ash or volcanic eruptions very often. But in 2010, so this is a map of the UK, this is the map of Europe here, the UK. Can you see my mouse?
Yes.
Perfect, thank you. This is a map of Europe and the UK, and just for context, I'm sat right about here right now. And in 2010, we had this eruption from Geological volcano in Iceland, and this produced a volcanic ash plume that, because of the wind direction, spread across Europe. So across Europe, we have quite high concentration of airports and of flight routes. And so this caused quite substantial disruption to aviation because we try and avoid aircraft flying through volcanic ash plumes. And that's because the melting temperature of volcanic ash happens to be very similar to the operating temperature of aircraft engines. And there have been incidences in the past where as you have air being ingested into an aircraft engine, it's bringing ash in with it. That ash has melted and coated the inside of an engine, which has significantly reduced the capabilities of that engine. And so you can imagine that there could be, with significant ash ingestion, quite significant impacts to an aircraft. And so while there's potentially direct impacts to aircraft that are flying through any ash, we try and avoid that by forecasting where ash is going to go. But it's also important to note that there's direct implications for aviation, and obviously, well, in relation to this event, there were significant economic impacts for the aviation industry, but there were also economic impacts further afield. And one example of that is, for example, the flower growing industry, the cut flower growing industry in Kenya. And they're reliant on moving their flowers by aircraft, and because the amount of aircraft in the air had significantly declined, it meant that they lost a lot of business, they lost a lot of money. So it's quite interesting to think about kind of the longer term and the chains of economic impacts of these sorts of events. But so basically, by looking at deposits on the ground and the impacts of ash in the air, what we really, to try and understand the hazard and the impacts, what we really need to do is understand the controls on ash dispersal, how ash gets into the atmosphere, and then hopefully forecast where ash is going to go, so we can be as prepared as possible. And so this is the same SEM image as before, but really what we're interested in is, how do we know where ash is going to go? And that's kind of a key question, and something that I'm very interested in answering. And so this comes down to understanding plume dynamics. And so on this slide, we have two very different plumes. And so when I'm talking about plumes, I'm talking about the vertical rise of this mixture of gas and ash from our vents up into the atmosphere. And we can see we've got two very different plumes here. So on the left, we have this example of a plume from Shimodaki in Japan in 2011. And we can see that it has quite an interesting shape, in that it rises vertically directly above the vents and then is bent over towards the left. And this is what we would class as a weak plume. The plume is being significantly impacted by the wind. So the wind direction is going in this way. So the wind is pushing the plume over, and that's affecting where the ash is going to go. And you can see underneath the plume that we have these almost fingers of ash that are being deposited. And again, that's also being affected by the wind as it's blown back away from the volcano. So what we're seeing here is that wind and atmospheric conditions can have a really big impact on what our volcanic plumes are doing. There's a balance to that, though, in that if we have very, very big volcanic eruptions and big plumes with lots of material emitted over quite quickly, we produce strong plumes. And so an example of that is the Pinatubo 1991 eruption in the Philippines. And here we have a very strong plume which rose up from the volcano, and you can see that it's rising vertically. You don't have any blowing over by the wind. And this actually reached quite high altitudes in the atmosphere before ash was then dispersed away. So we can see that depending on the balance between the strength of the eruption and the atmospheric conditions, that can have a key control on where ash gets into the atmosphere, and therefore how ash is dispersed. And so I wanted, I didn't know if this was too much, but I wanted to just give some background introduction into volcanic plumes and how ash gets into the atmosphere, just because it's quite interesting, and it also helps us to think about and understand the plumes for Anak Krakatau. But I promise not to spend too long on this. As I mentioned previously, during a volcanic eruption, we have an eruption of a mixture of volcanic ash and gas, and other things like water vapor and things like that. So we have our eruption event, and this material is emitted at very high velocities. And so when material is emitted at high vertical velocity upwards and out of the volcano. And this velocity is really important because the density of the mixture that's emitted at the volcano is much higher than the atmospheric density, which means that if we didn't have these initial vertical velocities, the material would essentially just collapse around the volcano and kind of froth over. And that's when we get pyroclastic density currents. But because we have these high velocities, this material is essentially kind of shot up into the atmosphere. And this mixture is very hot, so anything up to sort of 1,200 degrees. And as this mixture is being pushed up into the atmosphere, it's entraining ambient air, and this ambient air is cold, and as it's entrained into the plume, it's heated up, it expands, and that allows the density of this mixture to decrease to the point where the plume becomes buoyant. And at that point, we reach the kind of eruption column part of the plume, where it's a convective column, it's rising through the atmosphere, now not by the velocity, that initial velocity, but by buoyancy. And so we have this buoyantly rising plume into the atmosphere. And now here's where we have control of where ash goes. So the atmosphere is stratified in terms of density. And so the density of the atmosphere changes with height. And what happens is that the plume rises up through the atmosphere until it reaches the point at which the density of the plume is equal to the density of the ambient atmosphere. And at this point, because there's no longer buoyancy, the plume starts to spread out horizontally. And that's where you get your kind of umbrella clouds forming and your umbrella clouds forming. And so this is where we get this lateral transport of ash. And then it's from this laterally transporting plume that we have our ash deposition. And so that's just kind of a kind of quick intro to volcanic plumes. And those kind of, that description specifically relates to dry plumes. There are some differences when we have very wet plumes. So the humidity can change how, for example, the thermodynamics within plumes, and that's also important for thinking about Anak Krakatau later. So the key characteristics that control where ash goes, so that control the plume height, are the mass eruption rate, so the rate at which material is emitted at the vent. Things like emission duration, so how long the emission goes on for. The volume of material that's emitted. But there are also controls on deposition that are related to the particles. So if we think about how material is being deposited from the bottom of the plume, that's related to the terminal velocity of these particles, which is related to the size of the particles. So bigger particles get deposited closer to a volcano. It's also related to the density of particles. So denser particles get deposited close to the volcano, and the shape of the particles. So if you imagine if we have a spherical particle that's quite dense, that will fall out much quicker than something that is quite light, but almost has like a planar shape. And you can imagine that could quite easily be blown away by the wind, whereas something that's spherical is going to be less affected by that. And then we have atmospheric conditions, and the primary atmospheric condition is wind, so that controls where ash is going to go, which is really important, again, when we start thinking about Anak later. So I mentioned, I'm just going to have a couple more slides on the background of volcanic ash, and I mentioned earlier that I do a lot of work with numerical models, and I use numerical models to understand where ash goes, and these sorts of models can also be used to understand the hazards posed by volcanic plumes. And when we're looking at volcanic eruption columns and where ash goes, we separate the problem into two different problems. So we have one set of numerical models that simulate how ash gets up into the atmosphere. So this part of the problem. And then we have a separate suite of models that look at how ash is then laterally transported through the atmosphere, and they're called volcanic ash transport and dispersal models. And one of the reasons why we do that is that there's quite different processes that occur in those two different parts of the model of the plume. But also, if you imagine the kind of spatial distribution of these, so the plume obviously happens at one location or a small location, but ash can be dispersed over hundreds to thousands of kilometers. And so when you're taking into account, for example, the weather conditions on those types of scales, it's really important to have a kind of defined model for that purpose. And so I just want to give you a couple of examples of modeling of plume models. And so we have everything from empirical relations that relate what happens at the vent to what happens at to the top of the plume. We have 1D or integral numerical models, and these solve very simple equations for the conservation of mass, momentum, and thermal energy with height. And these enable us to investigate first order controls on things like plume height, which has when we're thinking about modeling the ash dispersion, that is the key input that we need. The good thing about these kind of easy, simple 1D models is they're computationally inexpensive, so we can use these and apply them very quickly, and even in an operational context. They're quite quick to run and to get results from. But the flip side of that is that they're simplified, so there are lots of simplifications that these models take into account. So I'm hoping that this video works. On the flip side of that are these 3D numerical models. And this is an example by a colleague, Matteo Cerminara, at INGV in Pisa. And these models allow a more complete solution to the equations that underpin the processes. So, for example, here we have our source at the base, which is emitting, in this case, it's emitting particles of particles with a diameter of 32 microns into an atmosphere. And the input parameters that he's used in this example are those that they expect to be the case for Vesuvius, the Vesuvius Pompeii eruption. And so this is trying to reproduce a real eruption by looking at how ash is transported into the atmosphere. I'm just going to, hopefully it'll let me just go back. And so what we can see is that this simulation represents well the eddies that form in these plumes. You can see the plume rising up to a maximum plume height, and then you see it starting to spread out. And this simulation also has a wind in it, so the wind is going towards the right. And you can see that as time goes on, the plume starts to spread out and the ash starts to disperse, the particles start to disperse in this direction. And so these are really novel, really neat numerical methods that are applied, that can be applied to understand plumes. And they allow us to understand some of the more intricate mechanisms that occur during eruptions. But the trade-off with these is that these are very computationally expensive. And so while they're really good for research purposes, they're not necessarily easily applicable for example, modeling specific events or for operational, trying to think about hazard, which requires quite quick model results. So Matteo has lots of videos on INGV, on YouTube. So if anyone wants to have a look at kind of different videos of these sorts of simulations, please do have a look. Okay, so hopefully what I've shown you is that talking about volcanic ash and plumes, so we've got volcanic ash, hazardous both in the ground and in the air. Ash can be transported over thousands of kilometers, and so it has quite wide-ranging implications. and controls on ash dispersion is related to, so it's related to how much energy we have at the base, the mass of the rate of mass emission at the vent, the characteristics of that ash. So if we have denser particles, they'll be deposited closer to source, but also atmospheric conditions, and in particular wind. So the wind conditions at the level at which the plume is dispersing controls where ash is going to go. So moving on to Anak. So Anak Krakatau is an interesting case. This is a photo of before the collapse in 2018. And what this shows is quite a nice plume. And I think that if we had a discussion about this, we could kind of agree that it would be a weak plume. You see it's not very continuous, it's kind of almost like a discrete puff, and we can see that it's already being affected by the wind. It's being kind of blown in this direction. And this sort of plume is very typical of the types of activity that we had at Anak previous to 2000s and the activity in 2018. So relatively discrete explosions related to strombolian activity, so lava fountains, lava flows, and with plume heights that are not massive, so maybe about 1.5 kilometers high. And then, as was mentioned previously by Mirzam and Igas, in the 22nd of December, that eruptive activity, we had quite a significant change in eruptive activity. And I'm not going to mention very much about the collapse because I know that, for example, Sebastian Watt and Alessandro Novellino talked about that previously. But essentially what occurred was on the 22nd of December, we had eruptive activity, kind of typical eruptive activity, strombolian activity with these lava fountains being emitted, lava flows, for example, and not significant ash plumes. There was the collapse of a portion of the volcano, and this led to a very distinct change in eruptive activity. And so this is what the plumes look like on the 23rd of December. So this is after the collapse. And here what we're seeing, we see a very, quite a white plume. There were lots of phreatomagmatic explosions, and what I mean by phreatomagmatic is that we have this interaction of the eruptive material, the vent, with the water around. The collapse had allowed the seawater to get into the vent, and that allowed for explosions, that produced explosions. It also produced a very water vapor-rich plume, and you can see that based on the colour of the plume as well. And so here we see this very white plume rising up over Panjang Island here, but we can also see that we can see the deposition. We can see that there's this kind of area of deposition in the sea, and we can see kind of, if you squint, you can see these what look like streams of deposits coming down from this plume. And so here are just some more images of the same plume, so from a similar time on the 23rd of December, and this time you can see the island of Anak, so you can see a bit better, kind of, sorry, mouse is getting very excited. You can see the relation of the plumes to the islands. So we have the open vents in the front here, we have lots of these kind of explosions, we have these cocktail jets that are forming, some small surges that are forming at the interface between the water and the plume. And we have the plume rising up and over, rising up towards the northeast, up and over Panjang Islands. And so this is really important. This is quite a nice observation that at these low levels, we can see that this plume it's not rising straight up, it's rising up and lofting over in a specific direction towards Panjang Island. And we can see also in the back, it's looking quite dark over here. We've got deposition that's happening from this plume in this direction. And because it's Friday afternoon, I thought I'd put lots of videos in. It's always good to look at videos of eruptions. So this is a video, it's a very short video around the same time again of a flight that was, I can't remember the height of it, I should have put it on. Oh, sorry, an altitude of about 1 kilometer. And again, you can see these cocktail jets forming. You can see this rising plume up and over Anak and over towards Panjang. And the other observations we can make is that it's a really humid environment, right? So there's rainfall that we can see across the camera. So there's lots of water in this atmosphere. And that's quite an important observation. And so we're really lucky in the sense that we have lots of these observations. So if you imagine if this eruption was happening at night, we wouldn't necessarily have these sorts of observations. So this is really important information for us to understand what's happening with the plume. And it's really important that we have those lower level observations, because when we look at the satellite information of where this ash went during this eruption or where the plumes went during this eruption, it paints a slightly different story. And so now this is Himawari data. And so we're looking down, these islands are the Anak Islands, and here we have Anak Krakatau in the middle. This is the coastline of Java and the coastline of Sumatra here. And this is a red, green, blue colour Himawari data set where each, so we have an image every 10 minutes starting from, apologies, this is in UTC, but starting from the start of the eruption on the 22nd of December. And what we can see is, if I just like that, so just to explain, at the edges, we're also picking up just meteorological clouds. So what I want to focus on is this region kind of over the volcano. And we can see that initially we have this, so if we're looking down on a plume, we have this plume that expands and then starts to disperse downwind. But the dispersion is happening very much in the south, towards the southwest. And this is an interesting observation because it's a very different direction to what we're seeing at lower levels. And these observations have important implications because if we only have satellite imagery, then we might assume that this is where the majority of the plume, the majority of the ash is going. But because we have these lower level photographs and images, we can actually see that actually there's a much more complex process going on here. And so this is, I was worried that videos might not work. So I have, this is an image that I've pulled from, again, Andrew Prater's work, but just synthesizes what was shown in that video quite clearly. So if we look at this picture here, number B, we've got the cross, that's the location of Anak Krakatau. Again, we're looking down on the plume. And this is a brightness temperature image showing the extent of the plume, again, being dispersed towards the southwest. There's also lots of information that was given and produced by the Darwin VAC. And I'll explain more about what the VAC does later, but they also provided information, again, from satellite imagery, using things like this brightness temperature to estimate a plume height of 16.7, about 16.7 kilometers. So pretty high. Prater et al. Also did some analysis that showed that this high level plume, so this plume at around 17 kilometers, had an ice signature. So it was predominantly composed of ice crystals, and it's thought that any ash within this plume was coated in ice. And then I kept this last image in E to say that while I'm talking about ash, there was also a lot of SO2 emitted during this eruption. And one of my colleagues is looking at modelling and looking at where the SO2 went during this eruption as well. And that's important because SO2 plumes also form during an eruption, but how the SO2 plume forms and disperses might not be the same as where the ash goes. So just because you have ash somewhere, you might not have SO2 and vice versa. So just a synthesis of that, for looking at the base of the plume, we have ash being deposited. We have the ash-rich plume, which is being dispersed to the northeast. We can see that it's very wet. You know, from the colour, we know that we've got from the colour and the fact that we've got this interaction with water. We know we've got lots of water vapour in this plume. And that likely means that we have quite high rates of deposition quite close to quite in this region. And then, so this is, you know, within the first couple of kilometres above the vent. And then much higher up, we have this, 17 kilometres, we have this plume that's being dispersed to the southwest. And what this implies is that, and I have the wind data, radioson data, and I can prove this later if anyone's interested, but what this implies is that at lower levels, we have one wind dispersing towards the northeast, and then at higher levels, we have a very different wind direction that's transporting ash to the southwest. So quite complex plume dynamics. What does this mean in terms of deposits? You know, it's always interesting to see these photos, but what does it mean in terms of what's on the ground? And so we were very lucky to be able to go into the field last year now, sorry, in August last year with Dr. Mirzam, and we were able to find some locations where we could find the deposits from this eruption. You can tell just by looking at this Google Earth image, which was taken after the eruption. And if you look at the colours of the vegetation on Sertang and on Rakata, the vegetation is still very lush, it's very green. Whereas if you compare that with Panjang, we have this kind of dirty kind of brown colour, and that's a reflection of both ash being deposited in this region, but also impacted vegetation. And that was something that we very much saw when we were in the field, is that vegetation on Sertang had been impacted by ashfall. And so when we look in the field, so this is in Sertang. So the other interesting thing about these points is that they're not equidistant, but they're not too far away. So they're both quite close to the volcano. And if we imagine that we've got this high level plume going in this wet direction, the low level plume in this direction, we would expect to have ash in both of these locations. And so if we look towards that southwestern direction on Sertang, and I don't have a photo of this because it was quite difficult to access, and not the ash was deposited among fallen leaves, so it wasn't a kind of distinct layer. But on Sertang we have an ash layer of about 1 to 2 centimetres thick, quite variable among fallen leaves. And this ash was formed of, was glassy scoria. So quite dense particles. We have textures that reflect phreatomagmatic source for these particles, so that reflect water interaction. And so some of these particles are quite blocky, we see. So this is imagery from a master student of Sebastian Watt's Kyra Cutler. When we compare that to the deposits on Panjang, we see a really different story. So now we're talking right underneath that kind of lofting plume, that low-level lofting plume. And here in this location, we were lucky enough to find what we think was the tsunami deposit. So we know that we're kind of at the base, at the start of the sequence. And above that, we have multiple different units with different colours, different grain sizes, and different layers. And this layered stratigraphy implies that we have a pulsatory phreatomagmatic explosions. We saw that, you can kind of see that from those videos, that you have these pulses of the plume and pulses of deposition. At this location, and we can see here that the thickness is much greater than that of Sertang. So while we were thinking about 1 to 2 centimetres, Sertung. Here we're looking at upwards of 20 centimetres of ash. So real difference in the amount of ash that's being deposited, which implies that this lower plume, which is dispersing towards the northeast, was particle laden, lots of particles, which were deposited quite quickly. And by the time you've got ash up into by the time you get up into this upper plume, we have much less ash that's able to deposit. And that all makes sense. So further afield, and these were I just wanted to give an idea about how far this ash went. We don't have any observations of ash towards the north, towards the southwest, partly because we're over water, but we do have observations and some samples of ash that Dr. Mirzam collected and that we're currently analysing to see how the ash at these locations compares to the ash proximally. And what we might be looking at is, we might be looking for example, that the ash at these locations is maybe slightly less dense and so able to be transported further, maybe slightly smaller, or maybe have slightly different shapes, so maybe be less blocky but more platy, and that might mean that it's transported further. But the interesting thing is that while the satellite imagery doesn't seem to imply that we have ash being deposited long distances towards these locations, towards the east, the deposits definitely imply that the ash got there. So it's one of those things of, satellite imagery is great and it tells us lots of things, but like all imagery and like all methods, it's not perfect, it doesn't show everything. And so that's why when we're looking at things like volcanic plumes, and particularly complex volcanic plumes, it's really important to bring together different streams of information. So there's lots of questions around the 2018 event. So there's questions, for example, as to whether the eruption led to the collapse, whether the collapse led to the eruption. It's a bit of a chicken and egg situation. But to try and think about answering some of those questions, what we need to also do is relate the plume and the size of the plumes that formed during the December 18 event to previous activity. Are these normal? Is this, a 17-kilometre plume, is that the typical behaviour that we see at Krakatau? Is that normal for what we see in the past? So as I mentioned previously, if you look through historical eruptions and historical information, reports from PVMBG, for example, what we see is that the activity is predominantly strombolian. So lava fountaining, emission of lava flows, and relatively discrete eruptions, so kind of short-lived eruptions with relatively low plumes. And that's kind of typified by this photo in the background. And so to try and look at this question of, are these plumes typical? Are those plumes from December 2018 typical? And what I wanted to do was get some data that kind of goes over a slightly longer period of time. And I decided to look at information from volcanic ash advisories. Now, volcanic ash advisories are an operational product, which are produced for civil aviation. They're produced to inform civil aviation of any ash hazard. And so global airspace is split up into 9 different regions, and each of those regions has a responsible volcanic ash advisory centre. And the Volcanic Ash Advisory Centre for Indonesia and for the region of Krakatau is Darwin-VAC, which is located in Australia. And the role of a VAC is to communicate with the Volcano Observatory to look at satellite imagery and use any observations that they have of eruptive activity to initiate model simulations of volcanic ash. And what they then do is use these model simulations, these observations and model simulations, to forecast where ash will go within the next 6, 12, 18 hours. And these are products that are given every 6 hours during an eruption. So so they're quite a nice source of information because they're given relatively frequently. They kind of record change in activity through time. And so what I've done is I've chosen to use these as a kind of source of information to compare activity at Anak through time. And so this is an example of a volcanic ash advisory. So this is the graphic that comes with an advisory. And here what we see is we have a volcano, Anak Krakatau. This is from the 23rd of December at the time of 10:20 UTC. And this polygon delineates the edge of, in this case, the observed ash at this time. And then these other polygons delineate the forecasted ash through time. These are forecasts that are defined from application of numerical models. And this is a simplified observation. And they also have information on the height of the plume. And because it's a product for aviation, this height is in flight level, which can be converted to what we're more used to seeing. So for example, kilometers. And so a flight level of 550 is equivalent to a kilometer, a plume height of 16.7 kilometers. And apologies that this image hasn't come out at the highest resolution. But what I've done is I've looked back at the data set from Darwin back until 2000. And the points are coloured according to, so all of the grey points are kind of the older ones or anything that happened after the 2000s, the kind of main phase of that 2018, early 2019 phase. The black points represent the activity. So the activity that led up to that December event started in July 2018. So the black points represent the advisories that were given kind of during that eruptive episode. And then the red points represent those advisories that were given during this December 18 event. And on this plot, each point represents one advisory. And I'm sorry, I thought I changed this. So across the bottom is the date, and up the side is the plume height. So this is plume height, and so we have 16 kilometers up here, and then these are the years. And so what we see is that in earlier activity, we have plume heights that are no more than 6 kilometers. So pretty low level stuff, you know, between 2 to 6 kilometers. And we don't really see anything that's much bigger than that. The important thing to remember is that because these ash advisories are produced for civil aviation, they're not necessarily looking at the very low level ash plumes. So, you know, something that's maybe a couple of 100 meters or 500 meters. And they're also not looking at gas plumes or, gas plumes. So they're specifically looking at plumes that might impact aviation, but that's quite good for us because we're trying to see if we have higher plumes that kind of relate to the ones that we saw in December. When we look, this has the right axes on, great stuff. When we look at the activity that occurred during this eruptions phase, so as I mentioned, the kind of whole, the start of this eruptive phase occurred in July 2018, and we can see that, so again, each point represents one advisory, and we can see that Darwin VAC were pretty busy during this time. So there were lots of advisories that were given throughout the months preceding December, but that generally show plumes that are still in the region of less than a couple of kilometers, with maybe maximum up to 6 kilometers. And then what we see is that when we get to these bigger plumes, when we get to these later dates, we're getting these much bigger plumes. So it's only then in December and January that we get these plumes up to about 17 kilometers. So what we can imply from this is that based on kind of this 20-year activity, and Anak's not a massively old volcano, so we don't have Anak Krakatau, the cone is not massively old volcano, so we don't have hundreds of years worth of information. But based on this 20 years worth of information, we can see that that activity that occurred in December really was something quite spectacular for this volcano, and implies that this opening of the vent to the water, but also this collapse which allowed for depressurization of any magma there, really led to quite an energetic eruption on the scales that we haven't kind of seen previously for this specific cone. So yeah, basically, based on Anak Krakatau, what we see is that we have observations and deposits that show multi-level dispersion. And I again want to highlight, satellite information is really useful, and it's particularly used, for example, in looking at large areas in global hazard and things like that. But it can also sometimes paint a simplified picture. It doesn't necessarily pick up all of the ash that is being dispersed during an event, and therefore, for the Krakatau event, we're really lucky that we have these images of what's happening lower level to help us to understand where ash is actually going. And what we can see is that while the high level plume is dispersing to the southwest, the majority of the ash is being deposited to the northeast, and that obviously has implications for example, the coast of Java. And that dispersion is controlled by wind patterns. The eruption heights from the 2018 events are much greater than previous activity that we've seen. So it's an interesting case study. One of the things that we're trying to do is to use those eruptive products to understand, again, why this was such a special event in terms of its size and the behavior. And one of the things that I'm currently doing is conducting numerical modelling of plumes, and specifically of this plume, to understand the plume dynamics a bit better. And so because there's quite a lot of things going on, so this interaction with water, it means that actually some of the modelling of this plume is quite complex. So that's quite fun to do. And that was what I had lined up to say, but I'm very happy to answer any questions or expand on anything that I showed. I hope I didn't talk for too long, or I talked for long enough.
Yeah, that's okay, Sandy, we can continue.
So the only other things, what did I have to show? This was the only other thing I had to show, was that I didn't want to show you too many graphs for a Friday afternoon. So this is essentially radiosonde data from for the date of the December eruption. And this, unfortunately, the nearest radiosonde is in Jakarta, so it's quite a long way away. But the radiosonde data shows us atmospheric conditions for the eruption. And essentially what we can see is the wind speeds with height, with altitude, and also the wind direction with altitude. And this is at Jakarta, but we assume that the kind of wind conditions are generally similar for Krakatau. And this information is open source, and I can let you know where I got this from. But essentially what we do see, if you remember, we had these that ash being deposited at that 17 kilometers. We see that when we get to these high levels in the atmosphere, we do have particularly high wind speeds, but also changes in wind direction. So we have around 70 kilometers, our wind direction is coming from the northeast, so it is pushing the ash to the southwest, and so this really helps us to explain some of the dynamics that we see in terms of where the plume is going.
Okay, Sam. Thank you very much for your nice talk. There is already a question from the audience.
Yeah.
Yeah, this is from Rudy Arif Satrio. The question is, what is the most dangerous impact of volcanic plumes, which is produced by volcanic eruptions such as Anak Krakatau, and how significant the impact for the people who live around the eruption zone?
So that's a really good question. So plumes are just one part of an eruption, right? So one of the conversations that I often have is how multi-hazardous volcanoes are. So volcanoes can have lots of different hazards that have are very hazardous. So we've talked about tsunamis previously and things like that. In terms of plumes, the hazards around volcanic plumes are related to, so if we think about ash plumes, they're related to deposition of ash causing damage to buildings. So for example, roof failure, things like that. And that predominantly happens quite close to a volcano. You have a lot of deposition. But there are also, so the hazard changes with distance from a volcano. So when you have a volcanic plume, most of your material is deposited close to the event. And so your hazards are much higher than they are potentially further away. There are also hazards related to gas plumes, for example, so SO2 plumes, which isn't something that I mentioned a lot about today, but lots of eruptions also have emission of SO2, and that can also cause quite big issues, for example, with health, so breathing difficulties and things like that. So there, yeah, lots of hazards. I think that the most hazardous are those related to the most hazardous in terms of short term are likely damage to buildings and impacts to health, but longer term you have impacts for, as I mentioned before, agriculture. It's very difficult, it takes a long time for agricultural areas to recover from deposition of ash.
Okay. Yeah, thank you, Sam. Yeah, because recently our government very concerned related to the impact from the volcanic eruption. They ask, maybe they ask university, not only ITB, how to manage post-disaster after the big eruption. For example, now we are facing the eruption for Sinabung as well as for Merapi. I think it's very important to get a better understanding about the volcanic plumes.
The good thing, so I think that was also why I wanted to touch a little bit on numerical modelling. So obviously I've talked about plumes and numerical models that are used for plumes, but there are also numerical models that can be used to look at hazard from pyroclastic density currents, from lahars, so there are different tools that can be used.
Okay, Sam. From the panelists, maybe Dr. Ida or Professor Amy, is there any question?
Well, looking at your explanation, I think maybe talking about the plume of, eruption, it's the hazard is rather in a health, isn't it? The health of the people.
I think in the sense from plumes from Anak, the main impact would be, so just speaking specifically about plumes, because obviously there's lots of other hazards, but the main impact would be potentially due to health, just because you have those, you have ash deposition and ash over Java.
So the dispersion is, we have to limit it. Well, I should not say that limited, we have to protect now, but we have to realize, okay, then the dispersion is that long, is it?
Yeah, so I think just to acknowledge, so I think that this event at Anak, the December event was much bigger than what is typical activity, and that is related to the collapse. So this was a very specific event, and I don't think that normally you have such long dispersion over such big areas. So I think the impact to Java was related to the fact that we have quite a much bigger event than we have previously. But yes, I definitely think that it's just knowledge of what the potential implications of ash deposition are. But there are also, so for example, in New Zealand and in the US, USGS have put together quite a lot of documentation on how to respond to volcanic ash deposition, how to clean up ash, for example, and there is information about how to respond. Obviously, it's not really very possible to try and stop ash being dispersed, but there's ways to respond.
I see. We're talking about you mentioned also the phreatomagmatic. Well, actually, do you mind to explain rather, because, well, actually I know nothing about the phreatomagmatic. I mean, what is the difference with the non-phreatic?
So what happens is that, so in a so we have kind of magmatic eruptions where we have material that's just emitted because we have fractionation, we have our material, our magma that's rising up, and we have our ash formed in that situation because as the magma rises, any gases in that magma expand and fractionate the magma around it.
Right.
And so that's a dry situation where there's no water involved. Whereas if you imagine for Anak, we have our magma, or our magma and molten material interacting with water, and that causes very quick fractionation. So instead of it just being these bubbles expanding, what you're essentially doing is cooling the magma very quickly because you're interacting with water, and that causes it to shatter almost. And so you have very different textures in that because of that as well. So it's essentially just shocking the magma and cooling it down very quickly by applying water, and then that fragments that magma.
So sorry.
And the result is that you have quite blocky particles, whereas when you have ash being produced from magma rising up and bubbles expanding, what your ash is essentially the kind of edges of those bubbles, and so there's very different shapes that you can get, and they're quite cool.
Is there any an impact for it?
A specific impact?
The dangerous, for example.
Related to phreatomagmatic?
Yes. If it happened.
Yeah, so there are differences in how ash is deposited. So when you have phreatomagmatic plumes, there's lots of water in those plumes, and that means that ash can stick together. It acts as a bind to stick together in the ash, and that means that you can have more ash deposited closer to the source of the volcano. So it changes how ash is deposited. But there are also impacts or hazards related to phreatomagmatic eruptions in the sense that because you have this water being displaced, we have things like tsunamis and things like the potential for tsunamis and things like that, because you have these explosions that are emitting quite a lot of energy, and that energy can be transported and transferred into the plume, or transported into the water, or transferred through the water. So the phreatomagmatic eruptions are more complex to stimulate, and the hazards are a little bit more complex than dry plumes.
Okay. Thank you, Samantha.
Thank you, Boemi. Thank you, Sam. Now we are going to the next question. Before we are going to the next question, I would like to say hi for my student and also for my colleague from CVGSM, the Center of Volcanology and Geological Hazard Mitigation, and also my colleague from University of Gajah Mada, Mbak Esti, and also Pak Heriadi, senior researcher. The next question is from Mbak Esti from UGM, University of Gajah Mada in Yogyakarta. Sam, would you please share your view on how eruption dynamic affect the sudden change of plume high from the other plume in December on December 22nd plume? Thank you in advance.
Okay, so So we're looking at comparing the plumes on the 22nd, which were relatively low level. On the 22nd, Anak Krakatau still has this cone, and the vent at which the material is being emitted from is like multiple hundreds of meters above the water level. And so there we're talking about a relatively dry eruption, a dry plume. We don't have this interaction with the water, and we have what the typical Strombolian kind of eruptions. So that eruption might be just due to bubbles bursting in the conduit. So they're kind of quite short and sharp eruptions. When we have this collapse and we lose a lot of that cone, and what was the vent is now underneath the water. And that means that we have a lot more energy being dispersed or produced because we have this interaction of the cold water with this very hot magma. So we have lots of change in energy dynamics and explosivity. But one of the other things that we're also investigating is that we have this unloading. So if we imagine we have lost quite a lot of this, quite a lot of the volume of the volcano, and that has been taken off what is the top of this volcanic system. And that will change the pressure dynamics in the system and change how the magma moves. And so one of the things that we're looking at, and I have to admit I'm not the expert in this, but is looking at the geochemistry and the petrology of the erupted material through time to see if this unloading has changed the rate at which magma underneath the volcano has moved up through that conduit, through that system to the surface. And so there's a balance of those two. I think there's a balance of those two kind of phenomena that affect and that produce these bigger plumes.
Okay. Yeah. So you mean that this is important for us to see from the, for example, microtextural evidence, so we can identify what's going. So what happened before the eruption with many high of the plumes.
Yeah, and so I think that's important, and also comparing the textures from events, earlier in 2018 to see the textures and the geochemistry and petrology of particles from earlier in 2018 to see what the kind of normal behavior is, if that makes sense. The normal rates of emission, the normal movement pattern of magma in the volcano, and comparing that with the deposits from 2018 to see whether, with the removal of this weight of material, all of a sudden we have an increased rate of magma to the surface.
Okay, Sam, thank you. So the next question is from Mr. Heriadi Rahmati, senior researcher, actually focusing on Tambora volcano.
Oh, nice.
Yeah. The question is, what is the main cause of the formation of plumes? Is it because there is a supply of new magma coming from the hot zone, or from the more deeper source? Yeah, thank you.
So the source of volcanic plumes, Ms. M, can you repeat the end of that question? Sorry. Is it from
the main cause of the formation of the plumes? Is it because of the supply of new magma coming from the hot zone, or from the deeper source?
So with Krakatau, I think it's just a new supply of magma. So we know this volcano was in eruption. It had been erupting for months before. So we know that there was like a supply of magma there already. We don't see any evidence or we haven't seen any evidence yet of any magma from a deeper source that implies that we have an additional feature that caused these eruptions, these volcanic plumes. But the volcano was already in eruption, and so there was already magma there ready to be erupted, and from pretty shallow levels.
Yeah, and I mean, in case Sam, if the if the eruption triggering by the chaotic process in the shallow level, as we found in the 1883 from Ember study, and then compare with the possibility of the Merapi activity, that we saw that there is no influence from the deeper source to the shallow magma chamber. So it will different with the plume characteristic if the source is quite different.
So would you have different plume characteristics if it was from a deeper source versus shallower?
Yeah.
Okay, so the plume characteristics depends on the dominant control on the plume characteristics is the rate at which material is emitted at the vent. So that's called the mass eruption rate. And that is controlled by the rate at which material is coming, up through the volcano. And so you can imagine that if you have kind of continuous, kind of shallow level material coming up, you might have normal continuous behavior. If you then have something that's coming up from deeper, that's additional, that's adding more material, that's destabilizing the system, then you might get more energetic plumes, and particularly if you have mixtures of different types of magmas or a different magma type. So, but that's related to the explosivity and the viscosity of the magma. So if we imagine something like basalt, where it's not very viscous, bubbles can move freely in that magma. During kind of strombolian basaltic eruptions, we have smaller plumes because the bubbles can expand quite well within that magma without breaking it, without making lots of ash. But then if you think about something like rhyolite or andesite, which is a different type of magma, it's more silicic, and that means that it is more viscous, it's more difficult to stretch, for example. That means that when the bubbles are trying to form and expand, the energy that's expended doing that, there's more energy, and therefore there's more energy during the eruption, there's more ash that's formed. The ash is slightly different. So there are kind of, I'm trying to essentially draw it with my hands. But there are kind of underlying controls on the type of plumes that depend on, for example, the geochemistry of the eruption, the magma type, and things like that.
Okay, so from your explanation, we can hope that the next eruption from Merapi maybe will be okay, will be small compared to the 2010, because there is no evident influence from the deeper part to the shallow magma chamber.
We can hope, but it's difficult to know.
Okay. Yeah, thank you, Sam. And then the next question from my student dari Hilmi Hasibuan. How much influence does air pressure have in controlling plume dynamics?
The air pressure?
Air pressure, the controlling plume dynamics.
Yeah, so there are controls on air pressure, because obviously the controls on air pressure depend on the height of the plume. So because your air pressure changes with altitude, that air pressure is one of the things that that controls the density of the atmosphere. So if you look at the equations that you use to define density, pressure is one of those inputs. And so your density, as your pressure changes, your density is changing in your atmosphere. And that kind of controls then, if you remember how we talked about the height at which your plume reaches is dependent on this relationship between the density of the rising plume versus the density of the atmosphere. And so because the pressure, the atmospheric pressure, the air pressure relates to the density, then that has a direct impact on that relation there. Does that make sense?
Okay, thank you. Thank you, Sam. Dr. Idan, maybe do you have any question related to the plume modeling.
Okay, thank you, Pak Mirjam.
Uh,
Okay, thank you, Samantha. It's very interesting presentation. My question, I interest with your data with the plum height. How you calculate the plum height?
So the plume height, yes. So actually prepared, yes. Hang on 1 second. So there are lots of different ways that we can calculate plume height. And so I put this slide together because I thought this might be a question. In the information that I was using, or the information that I presented, that is predominantly estimated by looking at using satellite imagery to look down on the plume. And what happens is you can estimate the temperature at the plume top, the atmosphere at the temperature of the plume top, and we have profiles of what we know the temperature of the atmosphere is with height. And so we can see what the temperature at the plume top is, and then we can relate that to these profiles and use that to estimate plume height. And so satellite imagery is something that's used a lot. But we also have different methods from the ground. So for example, things like using radar, different visual techniques to estimate plume height. Webcams, things like that. So you can align your webcams and measure them up to see, so that you can identify, if you have an observation of a plume, what height that is at. And we also get information from just pilots driving, flying past plumes when they can see them. So lots of different ways, essentially. The information that I showed you was from satellite analysis, but this is quite a nice overview of the different techniques that can be used to inform plume height.
Just in case on Krakatau, how you calculate the plume height? Yeah, because it's very, I saw on your data. Yeah, it's very, we have many plumes and then very short time. So, and how you calculate that data?
Yeah. So again, so lots of plumes, short time. So with, for example, Himawari, we have images every 10 minutes. So we can have, if you have a plume, we can have estimates of plume heights every 10 minutes. The information that I used was every 6 hours. So that can be the processes that are used to define the plume heights from satellite imagery can be automated. So that process can be quite quick once it's already set up and automated. Krakatau is, there is a reliance for Krakatau either on webcams, so there are webcams. I think PVMG has webcams in place. I often see photos of plumes. Or satellite imagery, because obviously there's not a lot of land around and at Krakatau, and if you have big plumes, you need to be far enough away to be able to see where the plume is going. So there are difficulties around that, but yeah, we can automate that process. So getting the plume height can be done quite quickly.
So one more question, is it okay?
Yeah.
Related to the on your model also, I mean, one of the parameter is using the volume of the eruption product. Okay? And then how you calculate also the volume of it?
Oh my goodness, that's such a good question. So the inputs for a numerical plume models, we'd be looking for plume height, we'd be looking for volume, things like that. When we are simulating operationally, when we're simulating plumes, so if we're trying to think about where ash is going to go in the near future, the we don't have to have an accurate, a very specific estimate of the volume, because the volume is related to how long an eruption goes on for and the rate at which material is emitted. So if you're trying to do an operational analysis, you might be thinking more about like, okay, we're looking at a 6-hour eruption, and then you can count, so you wouldn't necessarily need a volume in that sense. Now, if you were, so for example, we now wanted to model that Anak Krakatau eruption. And because we're simulating a specific event, we know how long it went on for, we know the plume height, we would want to know the volume. And what we would do is we would rely on field analysis of the deposits. So we go into the field, we would take as many measurements of the thickness of the deposit, or the thickness or the mass of the deposit at a location. And then there are tools and techniques that we can apply that would interpolate between those measurements, and then integrate under that interpolated surface. And I can send you information on this to estimate the volume. So the volumes, when you're looking at past eruptions, are very much based on deposits. When you're looking at modeling something that might happen in the future, it's an estimate based on what activity has happened in the past and what you think might happen, what's most likely to happen in the future. Does that make sense?
Okay, Samantha, thank you for your explanation.
Thank you.
Thank you, Pak Mirsyam.
Yeah, thank you, Dr. Ida. Pak Kristianto, Pak Chris maybe from CVGSM, is there any question? Or Mbak Estu, you have so many experience with Batur and Agung volcano in Bali. Okay, maybe there is no more question. Maybe the last question from me, Samantha. Yeah. Did we find something, or is there any specific relation between the plume height with the repose time of volcanic activity?
So is there any relation between the plume height and the first time of activity?
Yeah, with the repose time.
Repose time, okay.
Yeah.
So usually when we look at the relationship between repose time and volcanic activity, we're looking at the repose time and the volume or the magnitude of an eruption. And so we can see that, the longer repose times, that we would expect bigger eruptions. So we don't typically do that analysis with plume heights, but plume height is directly related to, there are empirical relations, and I can send you something on this. Yeah, I can send information on this if it's useful. There are empirical relations between the plume height and erupted magma, which the volume of erupted magma, that show that if you have larger amounts of the larger volumes of eruptions, you typically also have higher plume heights. So given that there's this relationship between the volume and repose, that it also makes sense that there would be some relationship between plume height and repose period, but it's not something that's necessarily been quantified.
Okay. Thank you, Sam. Okay. I think now we are at the end of the discussion, ladies and gentlemen. We have finished the guest lecture for the day. We have learned a lot today regarding the mini plume of Anak Krakatau. Thank you very much, Sam, for your time and also for your knowledge. May what we have learned today will be useful for us in the future, because we have so many homework in Indonesia, many active volcano. Recently, maybe we have Merapi, we have Sinabung, we have Semeru in Java. Before we close this session, we will take a photo together for the panelists. So please Okay. 1, 2, 3. 1, 2, 3. Okay, once again. Thank you. Let me to inform you that next week we will have the last guest lecture for this semester. So we'll continue next semester. Please check the date through the official Instagram of our Faculty of Earth Sciences and Technology ITB. For the recorded video, you can follow to our YouTube of our faculty. Thank you, Dr. Samantha. Thank you, Professor Emis Parka, Dr. Idam, and all the attendee. Thank you for everyone. See you next week. Stay healthy and have a nice weekend.
Thank you for having me. Have a good day.
Yeah,
Good night.
Thank you,
Sam.
Samantha. Thank you.
Ibu Emi.
Ibu Emi.
Yeah. Yeah, thank you, Sam. The audience asked about the possibility to have your material presentation. Is it okay, or they just follow through the YouTube?
Yeah, so I can. I'll cut out the bits that I didn't say, and then can I send you the compressed version, because otherwise it's quite big.
Yeah.
Yes, that's fine.
Okay. Okay. Thank you once again, Sam. So
Thank you very much.
in the near future we still have homework for anak Krakatau. Bu Emi, Dr.
Definitely.
Idam also will join in the study of anak Krakatau. Hopefully with you, Sam, and also from the colleague from UK.
That would be perfect.
Ya. Baik, terima kasih semuanya, akan saya tutup. I will close the resolution. Thank you, Sam. Okay, Sam, I will leave the Zoom.
Sounds good. I will. I'll email you with the presentation.
Okay. Anyway, is there any progress from our study about plumes from anak Krakatau?
So yes, we are. So Catherine, Kat, is doing all of the. I'm conscious that we're still live. Is that right?
Sorry.
Are we still on YouTube?
Oh, okay. Okay, stop. Just wait a moment. I will contact my staff. Just wait a moment. There is no response from my staff. Maybe we can talk later by email or by WhatsApp.
Let's do that, and we'll try and arrange a meeting to update. But very good to see you.
Yeah. Okay. See you.
See you
Bye.
soon. Bye.